Welcome everyone to the third eSafe Academy webinar titled e-THERM, an efficient solution for renovating thermal systems. I am Alexandra Pajic from Moverim, leading partner of the dissemination communication activities within the eSafe project. This event is the final of a series of 3 webinars called eSafe Academy, that is an engaging platform designed to share insights, foster dialogue, and explore innovative solutions in the field of building renovation. If you missed the first 2 webinars, they will soon be uploaded on our YouTube channel. eSafe is a Horizon 2020 project aiming to contribute to the deep renovation of EU building stock by developing an innovative market-ready system that combines decarbonization goals with earthquake resilience. What makes eSafe unique is its well-rounded approach. It doesn't just focus on structural and environmental improvements, but also keeps in mind indoor comfort, quicker, more cost-effective implementation, affordable financing, and minimal disruption of occupants. The effectiveness of this system is currently being demonstrated with 3 pilot buildings in Italy and Romania. Today, we will present a forward-thinking approach to upgrading heating and domestic hot water systems with sustainability and efficiency at its core. To do this, we will have with us our partners from University of Catania, who coordinates the eSafe project, and the University of Bologna, which is responsible for all activities concerning the definition and the design of the technical system. Our speakers for today are Giovanni Semprini, Associate Professor at University of Bologna, specialized in HVAC systems and building physics, and Gianpiero Evola, Associate Professor of Building Physics at the University of Catania, and Technical Manager of the eSafe project. They will illustrate us how the e-THERM system can increase the use of renewable resources in building renovations, supporting the transition towards low carbon energy. Also, they will present a decentralized solution for domestic hot water production designed to improve efficiency, flexibility, and user comfort. Before I pass the floor to our speakers, I would like to encourage all participants to submit their questions through Slido. We will have a final Q&A session at the end of the presentation, during which your questions will be addressed. You can access Slido by scanning the QR code, or you can follow the link in the chat. Think that at that point, before I pass the floor I will now pass the floor to Gianpiero, and yeah, the floor is yours. Thank you.
Okay, thank you very much. I will share my presentation. Okay, fine. Can you see it? Can you see the presentation?
Yes.
Thank you. So, good afternoon, everybody. My presentation is a general one, which wants to introduce the e-THERM system in the framework of the EU policies and the scope of maximizing renewable energy sources in heating systems. And for this reason, before coming to the e-THERM, I would like to recall the main EU policies and goals regarding primary energy consumption and decarbonization. A first key objective consists in reducing primary energy consumption in the building sector. And indeed, this would help contribute to reducing the greenhouse gas emissions. It would enhance energy security in the EU countries by reducing reliance on imported fossil fuels, but it would also improve the competitiveness on the EU economy because it would drive innovation and growth in the energy efficient sector. In this direction, progresses are being made. We can already observe a certain reduction of the primary energy consumption, but projections suggest that more must be done. So the current policies might not be sufficient, and greater efforts are needed in the member states to implement further and effective energy efficiency measures. Coming to the decarbonization, it is well known that the EU aims to climate neutrality in the energy sector by 2050. For this reason, the first milestone in 2030 is to reduce greenhouse gas emissions by at least 55% if compared to 1990 levels. The European Commission would also like to reach 90% reduction in 2040 as an intermediate step. And in the direction, the policy, there is a strong, consistent policy framework in Europe, starting from the European Green Deal, Fit for 55 package, Innovation Fund, so a series of measures and documents that provide a comprehensive roadmap and address also, invite the states to implement legislative measures in this direction. The problem is that one of the problems actually is that in most EU countries, the greatest part, for instance, in Italy, the 80% of the existing building stock has been built before 1990. So this means that the energy performance is on average quite low. Buildings need to be renovated. With buildings also there are thermal systems, but actually at the moment the average building renovation rate in Europe is around 1%, even lower in Italy, for instance. So the EU renovation wave, for instance, calls for at least doubling this renovation rate. So buildings must be renovated. We must find a way to renovate them effectively to achieve decarbonization. So what can we do to achieve decarbonization? Well, first of all, we must increase energy efficiency of buildings and thermal systems. Then once the energy efficiency has been improved, we need to deploy, so to use as much as possible renewable energy sources. In this direction, the EU aims, for instance, to reach 42.5 renewable energy share by 2030 in the energy sector. Then we need to phase out, to ban, to use as not too much fossil fuels. And a gradual process actually is ongoing in this sense. Once we do not use fossil fuels, then we need to use electricity. So we are assisting to an electrification process in several sectors, even in heating in buildings. So electricity is covering an increasingly large share of the energy needs, and electricity, of course, should come from, if possible, from renewable sources. The last measure, but it is not at the moment very mature, is carbon capture and storage. This is possible, or this is interesting in those sectors where other decarbonization alternatives are not still ready. Coming to phasing out of fossil fuels, we can say that several countries in Europe, for instance, Spain, Italy, Germany, Norway, Netherlands, are already working on that. So in the next years, in those countries, the use of gas, or fossil fuels in the heating sector will be banned, and those sectors will be electrified. In Italy, just to provide some examples about the use of renewable energy sources, in Italy there is a decree launched in 2011 and then updated in 2021 that establishes that new buildings and all large renovation of existing buildings must include the use of renewable energy sources to cover heat, electricity, and cooling consumption, according to certain criteria. For instance, the 60% of the final energy needs for the only domestic hot water service must come from renewable energy sources, but also the 60% of the total final energy consumption for DHW, space heating, and space cooling must come from renewable energy sources. And finally, all new buildings and large renovations must use renewable energy sources to produce electric power, electric energy, and the minimum electric power is proportional to the building area, to the floor area of the building, according to these coefficients that you can see in this slide. So meaning that from 2011, basically photovoltaics is almost compulsory in Italian buildings. What can we do to achieve these goals? Of course, we can use solar thermal systems, which helps providing 60% of energy for domestic hot water. But we can also use photovoltaics. This is also compulsory, according to what I said before. And finally, we can also use heat pumps. Heat pumps are an interesting technology. Now is very, very common in Europe. And as we can see now, heat pumps use renewable energy sources. How? Because they draw energy, free renewable energy from the outdoors, from the environment. But this happens only when they work in heating mode, so only for space heating and domestic hot water production. So if we consider, for instance, in this slide, an air-to-air heat pump, which provides thermal energy to the user, and if we assume that the seasonal coefficient of performance of this heat pump is 4, this means that 25% of the final thermal energy comes as electricity to feed the machine, but the other 75% is energy drawn at the evaporator from the outdoors. So we can say that 75% of the final energy is covered by renewable energy sources. Very interesting. So this is true, I can repeat it, for space heating applications and domestic hot water preparation. Instead, when working in cooling mode in the summer, the same heat pump, which is reversible, of course, has a seasonal energy efficiency, for instance, let's say 3. So in this case, heat is extracted from the indoor environments. If the seasonal energy efficiency is 3, this means that 33% of electric energy comes from electricity, and then all this thermal energy is rejected to the outdoors. Well, in this case, in this application, there is no use of renewable energy sources in the heat pump. So, how can heat pumps help us achieving the goal, the scopes of maximizing the use of renewable energy sources in buildings? In this pie chart, I showed a possible distribution of the final energy consumption in a high-performance building in Southern Europe. Southern Europe means cooling-dominated climates. In cooling-dominated climates, well-insulated buildings have low energy needs for space heating. Here it's 35%, but it can be even less. And the biggest share of the final energy consumption comes or is due to cooling, but also to domestic hot water. Domestic hot water becomes an important share of this energy consumption. So if we use heat pumps for all these services, we can say that the share of the final energy consumption coming from renewable sources is 75%. This comes from the previous slide I showed you, but 75% is only for domestic hot water, the yellow share, and the red share, the heating. So overall, it's 75% of the 60%, which means around 45%. We are not able to reach the minimum share, which is 60% according to Italian regulation. But of course, if we also install PV modules to assist heat pumps, well, in this case, things change. Well, if we assume that FPV is the fraction of electricity coming from PV modules, now this is the new calculation we can do, but in this case, we can easily reach 90%, for instance, of the final energy consumption coming from renewable sources. So the coupling of heat pumps and PV modules in a cooling-dominated climate is a really interesting option. Of course, if we want to make this system also cost-effective, we need to see at profitability issues, which means that we have to maximize self-consumption rates, self-consumption of the PV electricity, of course. So in this slide, I show the time frame of what happens in a typical residential premise. The red line is the time trend of the PV electricity production, which reaches its maximum at midday. Of course, here we assume that the PV panels are due south. The blue line is the distribution, the time trend of the electricity consumption from residential users, which reaches its maximum at night or at evening. So during the day, we have an excess of PV electricity, and we can self-consume a certain amount of this electricity, but then we have to fed the remaining part into the grid, which is not profitable because the grid does not pay that much the electricity fed into the grid. On the other hand, at night, we have to withdraw a considerable amount of electricity from the net, and we have to pay it. This is not a good situation to maximize cost effectiveness. But if we, for instance, use batteries to store the PV electricity, the excess of PV electricity in the day, we store it instead of feeding it into the grid. Then we use it at night instead of withdrawing energy from the grid. Well, this is good. This increases the energy, the cost effectiveness of the system. So the systems we are talking about need to maximize the storage capacity in order to maximize cost effectiveness and self-consumption rate. But in order to maximize the storage capacity, we can of course, we can rely on electricity and on batteries, but we can also rely on thermal storage. So heat pumps can heat the water, even if in that moment there is no requirement of thermal energy by the user. The heat pump can we can warm up water. Water is stored inside a tank, and then the users will draw water when needed. We have a decoupling between production and storage, and this can maximize also the cost effectiveness if we let heat pump work when there is PV electricity available. Now, normally thermal systems with heat pumps work like that. I mean, they have a storage tank normally, because the storage tank is important for as a hydraulic separator. So to separate hydraulically the primary circuit and the secondary distribution circuit to the user, also as a buffer tank. Avoid, for instance, also too frequent startups from the heat pump. Normally, designers of thermal systems should already know this rule of thumb. The minimum volume of the storage tank is around 10 to 20 liters of hot water per kilowatt of thermal power from the heat pump. This is what we normally do. But if we want to maximize this storage effect, we can increase the storage tank with respect to this minimum rule, let's say. One other thing I can mention is that the European market of heat pumps is experiencing a wide diffusion of heat pumps with environmentally friendly refrigerants. With very low global warming potential. One of these refrigerants is propane, R2290. Propane is actually a fuel, so it is flammable, but it is also a very good refrigerant fluid. It can be used with the due security devices, let's say, even in the heat pumps as refrigerant. It has global warming potential of only 3, so very low, and it has a very interesting feature. It can work, it let the heat pump work even with very high water temperatures, up to 70 degrees C, which in normal heat pumps with common refrigerants is not possible. Well, of course, in these extreme operating conditions, the COP of the heat pump will be lower than with traditional operating conditions. But it is still interesting, and it is very good when we want to produce domestic hot water, we want to use heat pumps for domestic hot water production. Since these two plots compare the operating ranges of a commercial unit with propane, the green areas, and with a traditional refrigerant, the brown area. You can see that the green areas are larger than the brown ones, so we can reach even 75 degrees Celsius on the hot side, on the domestic hot water side. But as I told you, COPs will be lower. For instance, in these plots, we can see the COP of several units, several domestic hot water temperature. For instance, in the summer, when the outdoor temperature is 30 degrees, with the 55 degrees hot side, we have a COP around 5, but this becomes 3.5 in when the heat pump, when the hot water temperature is around 70 degrees. In the winter, 10 degrees outdoor temperature, we have normally a COP around 3, but if we want to work with higher domestic hot water temperatures, the COP becomes 2.5. So we lose around 30% efficiency when we want to, if we want to work with very high temperatures. But this is still possible, which would not be possible with common heat pumps. Well, in this framework, our e-THERM system that we are developing and testing in the eSafe project is based on centralized air-to-water pumps that are assisted by electric batteries and large water storage tanks, centralized storage. So we store thermal energy and electric energy, both. We use refrigerants with low WP, so propane in this case. But what is interesting is that we also use a second level of thermal energy storage, which is decentralized. In each dwelling, we install a small storage tank, small slim storage tank called e-tank. My colleague Giovanni Semprini will talk about it later. And this tank is used to store domestic hot water locally. It also has a plug-and-play hydraulic module inside, which helps facilitate its installation. This is a scheme of what we are doing in our pilot in Catania. So you see there is a heat pump, there is an electric battery. I also report some numbers regarding their sizing. There is a PV system with 16 monocrystalline panels for around 6,000 watt peak power watt. There is a large centralized storage tank, water storage tank. If you see in this case, the size of this tank is 40 liters per kilowatt of thermal power. So it's twice as large as common installations. And there is a distribution line to 10 dwellings. So we install in each dwelling, we have 10 tanks, one for each dwelling. Here you can see the storage tank in the upper side of the heat tank and the hydraulic unit, the plug-and-play hydraulic unit, where all control systems, valves, and so on. Well, of course, control logics are very important to optimize those behavior, the performance of these systems, and this is what we are working on now. So with our e-THERM concept, we have a lot of opportunity because we can apply easily or quite easily in energy renovations, not only in new buildings, especially if the building already has a main distribution piping network. So we can use it. We can just replace the storage tanks, the generator. We can follow a plug-and-play approach also to the existing internal distribution network, internal, I mean inside the apartments. We can also connect, if this is the case, to an existing district heating network, which is what we are doing in Romania, in our virtual pilot buildings in Romania. We can use this system both for just domestic hot water preparation or for the combined heating and domestic hot water preparation. And risk low disturbance for residents. We do not enter inside their apartments. We work outside. We put this very slim tank outside in the balcony, and we can plug to the existing distribution network. What we need to improve, and we are working on it, are the control logics, the size of the water storage tank, but also the battery in order to maximize the PV self-consumption rates and the cost effectiveness, of course, of our system. So further details about the e-THERM, e-tank, and its use for domestic hot water preparation will be told by Giovanni Semprini. Thank you very much.
Thank you, Gianpiero. Thanks for your preliminary presentation about our system called e-THERM. Now I focus focus on domestic hot water production. Is one important part in our project because the energy used for domestic hot water production currently accounts for approximately 15 to 40% from north to south Europe, and from old to new buildings, very large difference of energy consumption for DHU production. But as a thermal insulation and also tightness of envelopes improve, the share of energy devoted for space heating and cooling tends to go down, making the domestic hot water dominant energy load in new retrofitted building or new building with higher class A1, A4. The energy load, the energy consumption for domestic hot water is as about 50% of the total energy consumption. Thermal energy consumption.
You didn't share the presentation.
Sorry, I have to share my slide.
Yeah. Thank you.
Thanks. Okay.
We can see
okay.
it.
Okay. Is okay, Gianpiero?
I can see it.
Can you see the slide?
Giovanni, we cannot see your monitor.
Okay, fine.
Yeah, now it's working.
Okay, thank you. It's okay now?
Yeah, perfect. Thank you very much.
Thank you very much. Sorry for let's say also many studies in the literature report that the energy efficiency of domestic hot water system have a significant is surprisingly low, and a significant amount of the heat is lost from the hot water before it reaches the draw-off points. And this happens especially in case of centralized domestic hot water production, like in the picture. That involves a large storage tank and a large pipeline and the recirculation line operating 24 hours a day. And the hot water at higher temperature circulate during all day, producing a very high thermal losses. In old buildings, the pipelines are poorly insulated. This is a very big problem, also because the pipeline are inside the building structures, and it's very difficult to improve the thermal insulation. Concerning the domestic hot water consumption, daily domestic hot water patterns present typically two main consumption peaks that occur in the morning when people wake up, and in late afternoon, in the evening, when people return home from work or to school and before to sleep. And one investigation conducted in 2008 by the International Energy Agency provided information on typical domestic hot water consumption, and for different European countries and also in USA. And from this analysis, the consumption range from 100 to 120 liter a day in dwellings with 100 square meter of area, considered 45 Celsius as temperature. Also, another important aspect is to evaluate that in terms of energy flexibility, and it should be highlighted that the domestic hot water energy needs are the profiles, as you can see in the picture, not completely match with the energy availability from renewable energy sources like a solar system. And this is an important aspect when we make an energy analysis, and as Professor Evola showed in the previous slide, that in the early morning we have a higher peak, not only for heating, but also for domestic hot water production, and in the early morning there is not available energy from solar system. And from this aspect, it's clear that it's necessary to implement a solution to limit the energy consumption related to domestic hot water. First, we can use sustainable production technologies, including technologies that exploit renewable energy source systems. Gianpiero talked about heat pump system, air to water or water to water, or today there are also multi-purpose units that simultaneously produce cold water in summer and hot water during for domestic hot water. But we can use solar system, we can use also thermophotovoltaic system producing both electricity and thermal energy. And another important aspect is the use of a suitable thermal storage system with increased thermal capacity. Today, there are many experiments using phase change material inside the storage tank in order to increase the capacity of storage, of thermal storage. Another aspect is the reduction of heat losses from the hot water distribution system by optimizing pipe distribution, increasing thermal insulation when possible. And as I said before, in existing building, this is quite complicated to increase to the performance of the pipes because they are embedded in the wall, and only limited intervention are possible inside the thermal power plants. Another possibility to optimize is the recover the heat from wastewater at various levels, for example, through heat exchanger downstream the hot water discharge. But there are only in the stage of experiment at this moment. Last aspect, but I think probably the most important one, is to reduce the water consumption. Occupants' behavior measure would have a significant impact on residential energy use compared to the type of heat source of supply temperature. It should be remembered that in general, the hydronic system, not only for domestic hot water, but also for cold water services, are sized to ensure water flow up to 2 liters per second. But the actual flow rate depends on the effective pressure of the network. Then in a larger condominium, there are there can be a significant difference in pressure, and a very high flow rate can occur when the taps are open. And for this reason, it's important to reduce the flow rate to limit not only water waste, but also energy waste. Simple solution, like in picture, can be use a tap sprayer in order to reduce water consumption, in order to reduce the flow rate of the water. But also the behavior of the user is very important. First, by reducing the time of using hot water or the shower, reducing the consumption, let's say. Second, important aspect is to decrease the draw of temperature of domestic hot water. Some users use water at 50 up to 50 degrees. Normally, it's possible to use at 35, 40 degrees. Third aspect, we can use hot water period in the period in which the thermal energy is directly produced by renewable energy source. Is important also for the future important aspect in order to match, let's say, the energy consumption with the energy production from renewable energy source. That means that the user must adapt to change their habits in order to change the consumption per period. As shown by Professor Evola, this is the general solution for domestic hot water, using heat pumps, using decentralized storage tank, photovoltaics and batteries for the production of electric energy. In the retrofitting of existing building, we use the existing distribution pipe network. And one important aspect is use the building automation control and the building management system in order to optimize the use of renewable energy sources according to user consumption. Also, obviously, it's possible to integrate our system with different technologies, also with the solar thermal panels and so on. This is the same general diagram for the production of domestic hot water. Just focusing on the main decentralized system called e-THERM. The storage tank characteristics is a flat storage with a volume of 140 liter. This is, as you can see, is a flat design we watch developed by a partner, by big partner of the project. It is stainless steel and is built with the 5 pieces of vertical oriented pipes. And the central pipe is equipped with a screwed flange and equipped with an heat exchanger, which is connected to a 2-pipe hot water network system powered by the central heat pump. Recommended flow rate within the heat exchanger range from 150 to 300 liters per hour. Is there also an electric heater for about 1.5 kilowatt to ensure periodic high temperature prevention the Legionella disease. Standard thermal insulation is with polyurethane rigid foam, but if we wanted to increase the insulation when the installation of the system is outdoor, it's possible to add also vacuum panels in order to increase the total thermal insulation of the system. In this picture, in the upper picture, you can see the infrared images during the process of charging of the tank. You can see the started from the central coil, the temperature increase from the higher part to the bottom part of the storage tank. In the second picture below, second picture illustrates the time evolution of the tank's temperature for the case with the mass flow rate of 300 kilogram per hour and supply temperature of 45 Celsius. And the picture demonstrated that the transit temperature stratification inside the tank and showed that the full charging process of the tank takes around 70 minutes. However, the temperature of domestic hot water at the outlet port reach the maximum values much sooner, let's say at around 40 minutes after the beginning of storage, when the temperature starting from 10 Celsius. The picture also shows the good agreement between the experimental and the numerical results of the analytical model of the storage tank created in Transist with the Transist software. The hydronic module main components, there are outflow valve, thermostatic three-way thermostatic mixing valve for the limitation of temperature for the domestic hot water supply line into the dwelling. Also, polyphosphate dispenser that limits the lime scale formation in the domestic hot water system and also in the device connected to it. An ultrasonic heat meter to measure the energy consumption. And also in the control cabinet of the hydraulic unit, there is an electric and electronic cables installed and wired to all the components. It also includes a PLC. With this PLC, it's possible to control and monitor the activities of the e-tank system. There is also a network connection by different protocol, but normally by M-bus protocol. And this connection enables communication and data transfer with the central control system of the building in order to manage all the e-tank of the building. Special consideration about control system, the control strategies must ensure the supply of the individual apartments with hot water. This is the main goal, obviously, to supply the correct values of temperature in each building. For the general solution with both heating and domestic hot water service, a two-pipe network can be considered where the hot water produced in the central thermal plant could be used alternatively for the heating and also for domestic hot water production of a tank. This can be considered when simultaneous operation of the supply network is not always necessary, as during days periods when heating is off or attenuated, and the tank charges can be activated. Is it typical in many standard European standard that the heating system is not working continuously during day, and when the system is off, it's possible to charge the tank. Then typically the two times a day is possible to use the hot water from the pump for the charging of the e-tank system. During the heating season, the system can be operated at a far lower temperature. For example, when the heating system has underfloor heating, and then it's possible to modify the temperature of the main system from higher temperature, 55, 60 degrees, when we have to charge the domestic hot water, to lower temperature when we have to proceed with heating with the radiating system operating at a very low temperature. In the real pilot of Catania, with only domestic hot water production, the outlet temperature from the heat pump and also the tank set point are changing based on the availability of renewable energy source from photovoltaics and batteries. Then we consider the possibility to change the supply temperature according to availability of free energy from photovoltaic system. This is some picture of the possible installation of a tank. Normally, it's possible to install in indoor size, better in proximity of existing distribution manifold, or is possible, like in Catania solution, outdoor on balcony, for example, when there are more spaces for the installation. There are some picture of the installation in Catania. Also, we created beam elements in order to have possibility to drawing the system in different configuration. Then concluding some preliminary results based on simulation, not measurement. Measurement are currently proceeding, and there are preliminary results based on transit simulation. Here you can see the input data. We consider 12 dwellings with different occupation, with 1, 2 person up to 5 person for each dwelling. We consider a air-to-water pump with a seasonal coefficient of performance of 4.5, main storage tank of 1,000 liters with a set point of 60 Celsius. The set point of each tank in each dwelling set at 50 Celsius temperature. For the consumption, we create a MATLAB code. We develop a MATLAB code to define the domestic water consumption profile, taking account the number of residents up to 5 persons per dwelling, also considering monthly variation factor. And the basis is that we consider a mean annual consumption of 45 liters per person. And in this picture, you can see the different profile, our profile for the different apartments of the building. In the simulation, in the preliminary simulation, we consider the charging of the tank when the temperature is lower than set point temperature, and the charging period can be considered continuous or 3 times a day. Here's some results. First, is important when we decided to move from the traditional centralized system to the decentralized system to verify that the temperature is continuously available in each dwelling. Then we make a simulation for, you can see 3 different profile of temperature of domestic hot water. With 1 occupant up to 5 occupants, it is obvious when there are more occupants, the charging period increases, blue line. We compare the 3 different temperature with the inlet temperature of the main storage is set at 60 degrees, or when the temperature of the storage is set at 55 degrees, like in the second picture. In this slide, there is a comparison of the consumption, the electric consumption and thermal consumption of the system. With 2 different solutions with continuous charging 24 hours a day, or considering just daytime charging from 6 to 22. What is important to analyze that In the actual case, there are the decentralized electrical system with a higher consumption up to 13,000 kilowatt-hour a year, while moving to the e-THERM system, considering it pumped and the decentralized system, the electrical consumption are around 6,500 kilowatt-hour per year. It's also possible to, we showed the comparing the thermal losses for pipes, for the tanks and the main storage. It's obvious that the thermal losses of pipes is important depending on the distance, the length of the pipes. This slide showed the annual required primary energy and the share of renewable source in the proposed domestic water system for 3 different scenarios. The first scenario is considering the total electrical energy supplied by the external grid, the first case. Second case, by using a PV system without battery. And third case, we use a PV system in conjunction with the battery storage. The picture shows that the total primary energy for external grid case is about 28 megawatt hour of year, of which 54% is renewable. Considering photovoltaic, the photovoltaic reduced the amount of primary energy to 24 megawatt hour with a renewable share of 66%. And with the battery, the quota of renewable is reached around 82% of the total primary energy. This is a final slide just to show the impact of drop-off temperature. This is important because the user can have the possibility to choose the proper temperature, and we can make some simulation considering different drop-off temperature from 37 Celsius to 42 Celsius. And you can see that is evident the impact of the small increase in the drop temperature of domestic hot water by user on the total required energy consumption. And the rate of change in the energy consumption by variation of temperature is not the same for different scenarios. We consider 3 typical scenarios with 1 charge a day, 2 charge a day, or 3 charge a day. And normal tendency trend is that if we increase the temperature of domestic hot water, drop-off temperature, the energy consumption is greater with considering 1 charge a day. But for example, in the second scenario, with at 38 degrees Celsius, the second solution, 2 charge days, presented the lower energy consumption, requires 19 kilowatt hour a year, less energy than the previous the first case. This is the last picture, and I thank for the attention.
Thank you. Thank you, Giovanni and Gianpiero, for joining us in discovering the e-SAVE technologies and their applications. Now, I would love to open the floor for questions. If you haven't already submitted yours on Slido, there's still time. You can scan the QR code, or there's still the link in the chat. So, oh, I see we already have some questions here. Should we start with one of those? How does the e-THERM compares to other traditional systems? For instance, does it perform better than traditional centralized system for domestic hot water? I don't know, between Giovanni and Gianpiero, who'd like to answer to that one?
Well, I can answer this question, but I would like to share a slide to make my answer understandable. So, just to understand, what is the difference between our system and the traditional centralized domestic hot water system? Well, the difference is basically the presence in our system of this decentralized heat tank. So in a traditional centralized DHW system, the hot water in the centralized storage tank is drawn by the users and used. So the users touch the water inside this large solar tank. In this case, to prevent Legionella, by law in Italy, for instance, this water must be kept at least at 60 degrees Celsius. Instead, in our thermal system, the water coming from this tank is technical water. It is used to charge with thermal energy the tank. And the users draw water from this tank, which means that inside the large centralized tank, we don't need to provide Legionella protection, and we can use lower temperatures. For instance, I don't know, 55 or even 52 degrees instead of 60 or more. This is important because heat pumps in the e-THERM system can work with lower temperatures and then with higher COP. This is the first difference. The second difference is that while in centralized systems, water circulates in the pipes just when there is a when the users need water. In the e-THERM, water circulates more frequently because we have to thermally charge the e-tank, which means that the e-THERM system has more heat losses. So at the moment, according to the studies we have conducted so far, the two systems are more or less equivalent. So e-THERM has higher heat losses, but can work with higher COPs. And at the end, the energy consumptions, the electric energy consumption are quite similar. But these results can be improved because at the moment, we didn't optimize the sizing of the tanks and the control logics. So we have room for improvement. So we are confident that once we optimize the sizing and the control logics, our system will have lower electric energy needs than traditional systems.
If can I add something about this consumption? Let's say in this solution, the centralized system, I think is very, very interesting with many probably in North countries, in North European countries. Let's say when there are very low temperature during winter, and when they use a higher temperature in the pipe network, and using just one pipe network for both heating and charging domestic water can be very reducing the thermal losses during the on-off period. In our simulation, we make some simulation for Bologna, let's say middle region. The energy consumption from traditional centralized system and the domestic water are quite similar, but reducing, moving to north countries, these advantages are very, very, very high. And also another aspect is that you can pay, is a very another important aspect. You can pay only what you consume. Let's say in traditional centralized system, people pay also for, let's say, indirect consumption for thermal losses. In existing building, this amount can be also reach 50 to 60% of the total expenses. And the system reduce a lot of thermal losses and reduce the indirect expenses of the bill. This is very, I think, very important to highlight and to moving this towards this solution.
Okay.
And the second, also there is a second question about the possibility to use a solar assisted system for domestic water production during summer condition. Gianpiero?
Well, I remember we have talked a lot about what happens. I mean, if we talk about summer conditions, I guess that we think that there is a cooling, space cooling need. So we need at the same time to produce cold water for space cooling and hot water for domestic hot water preparation. Well, in this case, I remember, Giovanni, we have discussed it, and if I'm not wrong, we understood that the best thing is to have two heat pumps, one which works in cooling mode to manage space cooling, and the other one for domestic hot water. So two heat pumps and two separate storage tanks.
Yes, I think it's very important to make the preliminary energy audit of the building before defining the final solution. Very important to evaluate the consumption, better evaluating typical user the profile, hourly profile of the consumption in order to optimize the solution. We know that heat pumps works have different performance for different temperature, and it's very important to know the energy consumption, the domestic hot water, the energy consumption for also for heating, also for cooling. The general e-THERM solution have possibility to choose a different type of heat pumps according to the real needs of the buildings, according to the location of the building also.
Oh, then I see we have another question. Did you already define some criteria to optimize the sizing of both water storage tanks and the PV batteries?
I can answer, I guess, because I said something about that. We are working on it. We didn't already define criteria, but what we are doing in Catania is using a water storage tank, which is twice as large as we would have used in normal application. So we are working with around 40 liters of hot water per kilowatt of thermal power. But we think that even larger volumes would be better. But we need to study it. We have a PhD student who is working on that. And coming to the PV batteries, I don't have an answer. In our application, we used more or less common sizing criteria. So we have 10 kilowatt hour with a PV power of around 6 kilowatt. But we cannot say more than that at the moment. Giovanni, I don't know if you have some.
Yes. Let's say the answer can be quite complicated because today we have to think not only at the building level but at district level. Let's say if we have a higher production of electricity from PV, probably we have to share this electricity with the grid, and you know that if there are too much production of renewable, it can be problem for the grid sometimes, and then I think the correct choice in the future will be not analyze the single building, but making an analysis at district level, considering also the main cabin of electricity, in order to have a better matching between consumption district and the production for the building connected in this grid. But considering the single building, I think our choice make in the Catania is probably the better, also considering the cost, in order to not increase too much cost. Concerning the water storage, it's clear that bigger is the storage, better is to store the energy, but the problem is the size, the space available in the building. In our case, we put the storage on the roof, but also there is limits from structural point, and then it's not possible to increase too much the size of the storage tank, let's say.
Then I see we are left with the last question. I don't know if you would like to add something more on this. Someone of the speakers, or
Is it the same question as the first one?
Yeah, like pretty similar. So
yeah, it seems the same one.
So maybe it was left from before. Then okay, no problem. So at this point, if I don't see other questions in the chat, so I think that we are done with the questions. And I would like to thank our speakers, Giovanni and Gianpiero, for today's webinar, for today's episode of this series. And also I would like to thank all the participants who joined us today.
And thanks also, Alexandra, to you also, Veronica, for moving me to organize this webinar. Thank you.
Thank you.
Thanks. Thank you very much.
Thank everyone. Enjoy the rest of the day.
Bye-bye.
See you. Bye.
Bye. Have a nice day.
Bye.